Okay, so now that we know how to do differentiation, what we can do is apply it in a graphical situation. So for example, if we take an xy Cartesian plane like this, and I give us some functions to plot onto this Cartesian plane. So in the red, we're going to say that f of x is equal to x cubed, and that is going to look something like this. And in blue, we will say that g of x is equal to negative x squared plus 4x takes 6. And that is going to be a quadratic down there, looking something like that. And in the green, we're going to say that h of x is equal to x take 4 squared, add 3. And that's going to be a quadratic up here looking like that, something, okay? And we're going to look now at what we call the critical points. Critical points of a function, okay? The critical points of a function are when the gradient is equal to 0, okay? And you might be able to see now where differentiation is going to be important, because we know that we can use the derivative to find the gradient of nonlinear functions at any given point, okay? And we're going to find it when the gradient is equal to 0. So critical points. So where on these curves is the gradient equal to 0? And I will draw them in orange. Okay, if we come over here, it's equal to 0 here. The gradient's equal to 0 on the red line there, and the gradient's equal to 0 on the green curve there. So they're called the critical points. So critical points are in orange. And why is the gradient equal to 0 there? Well, if we draw a tangent at those points, we just get horizontal straight lines. So if you think that you're walking on a footpath, okay, and there's no incline, it's just flat, then there's no gradient. The gradient is equal to 0, okay? So there are critical points. And there are 3 types of critical points that we have, okay? We have what we call a local maximum. We have a local minimum. And the last point is what we call a horizontal point of inflection. Horizontal point of inflection. And that point of inflection bit is sometimes abbreviated to POI, or the whole thing sometimes abbreviated to HPOI. Okay, those things mean horizontal point of inflection. So can we label our critical points on the red, the green, and the blue curve as either local maximums, local minimums, or horizontal points of inflection? Okay, remembering that a local maximum I like to think of being sort of like being at the top of the hill. At top of a hill. And a minimum I like to think of being at, say, the bottom of a bowl. So that might help you find the local maximum, the local minimum. Okay, the local maximum is going to be on our blue curve. This here is the local maximum. You're at the top of a hill, right? The local minimum is going to be on our green curve, where you're sort of at the bottom of a bowl. Okay, so if we highlight those, I don't have a dark blue, but local maximums in the blue there, and in the green, we have our local minimum. And in the red is what we call a horizontal point of inflection. Okay, so that there is going to be our HPI. Horizontal point of inflection there. So we can, I don't have a red highlighter, but I can underline this in red. Okay, so there are different types of critical points. And if we want to look at why, technically why they're local maximums, minimums, or horizontal points of inflection. If we look at the y values either side of a local maximum, so here and here, okay, both the y values are lower than our critical point, which means, if we move to the left of the critical point, our function's going back down. If we move to the right of the critical point, our function's going back down. And likewise, on the green one, both the y values either side of our critical point are above, they're greater. So if we move there, we're going up, and if we move to the left, we're going up. Okay, meaning that critical point is a local minimum. And the horizontal point of inflection, well, if we look to the left of our critical point, we have a y value that is going to be slightly lower as to if we went to the right, where the y value is slightly higher. Okay, so that means if we go to the right, we're going up. If we go to the left, we're going down. Okay, so that they're not both the same. Okay, so that is what we call a horizontal point of inflection. Okay, so how can we find these? How can we use this formula here, or these formulas here, these functions, to be able to give the coordinate points for these critical points? Well, we use our differentiation. Okay, so if we start off with the red one, f of x being equal to x cubed. So we'll come down here, f of x equals x cubed. And I'll write the other ones whilst we have them there. G of x is equal to negative x squared plus 4x take 6. And in the green, we have h of x is equal to x take 4 all squared plus 3. And we're going to come down here and we're going to tackle these one at a time. Well, what we're effectively asking to find the critical point, remember, the critical point is when the gradient is equal to 0. So effectively, we can turn this into a worded question. Say this is f of x, x cubed, and say when does the gradient equal 0? Well, the gradient is equal to 0 when the derivative is equal to 0, right? So what's the derivative of f of x? Well, we can use the limit law theorem, or if we want to use a shortcut method, that's going to be much better. We can say that a is equal to 1 and n is equal to 3, so we're going to get 3x squared. And we want to know when that is equal to 0. So we solve this part of the equation here. So if we divide both sides by 3, we get that x squared is equal to 0. And that means that x is equal to 0. And if we want to know the y value when x is 0, we put that back into our original function. So f of 0 is 0 cubed, which is 0. So we get the point 0, 0 for red. So if we come over here, we get the point, we can label this 0, 0 in red. And for our blue one, okay, again, we're looking when the gradient is equal to 0. That's going to tell us our critical points. When does the gradient equal 0? Well, that's going to equal 0 when the derivative is equal to 0. Okay, so the derivative of g of x is equal to negative 2x plus 4. And then that minus 6 turns into a 0, so we're not going to worry about writing that in. And we want to know when that is equal to 0. So solving this part of the equation again here. So if we take 4 from both sides, negative 2x is equal to minus 4. And we'll divide both sides by negative 2. X is equal to 2. And when x is equal to 2, we want to know what g of x is equal to, or what y is equal to. G of 2 is equal to, in this case, minus 2 squared, plus 4 lots of 2, take 6. And that's going to give us minus 4 plus 8 take 6. And minus 4 plus 8 is 4, take away 6 is minus 2. So we get the point 2, comma, negative 2. So we can take that up to our blue critical point and label that to negative 2. And the last one is going to be in our green. So we'll come over here and we want to know when the gradient of h of x is equal to 0. Well, that's when the derivative of h of x is equal to 0. So the derivative of h of x, and if we look here, we don't have this in the nice formula or in the nice format of ax to the power of n. Okay, this isn't in the format of ax to the power of n. So we have to expand these brackets out. So we get x squared, take 8x plus 16 plus 3. And now this is easier to differentiate. Okay, we can simplify that 16 and 3 to a 19 and then differentiate it. Okay, so, that there is still what h of x is equal to. Okay, we've just expanded out those brackets and now we're doing the derivative of that. We're going to get, for this part, 2x, take away this part here, 8, and then the 19 just becomes a 0. And again, we want to find out when the derivative there is equal to 0. So if we add 8 to both sides, we get 2x is equal to 8, which means x is equal to 4. And if we want to know what the value for y, or h of x is, we put that up here. So h of 4 is equal to 4 minus 4 all squared plus 3. Well, 4 minus 4 is 0, and square that, you just get 0. So we're left over with 3 here. Okay, so we get the point 3, 4. And if we go over to our green point, we can label that as 3, 4. Right? And a little note that I want to make here is this is a quadratic. We should see that this green line here, this green curve is a quadratic. And it's in the turning point form of a quadratic. Remember that the turning point form says that if f of x is equal to x take p squared plus q, then the turning point is equal to p comma q. So we should expect that the turning point in this case, which is a critical point, the turning point, okay, it's when the, like a maximum or a minimum, okay, they're turning points, P comma Q. So with as, x take 4 squared plus 3, this is our P, and the 3 is our Q. So we should be labeling our turning point as 4 comma 3. And I've written this wrong down here. We said that should be 4 comma 3. See how checking it is important, right? Because I've made a little mistake there. This point up here is 4 comma 3. Okay, I've written them the wrong way around. We found that that was our x, and this is our y. I'd written them the wrong way around, but by using the turning point formula and just checking, we can see that this should be our turning point. And by the answers not marrying up, okay, it makes sense for us to check. Okay, so that's it for this short little video, okay? Just looking at what critical points are and how to use derivatives to find them, okay? But now in the next video, what we're going to look at is, well, what if you don't have a graphical representation? So I don't draw you those graphs, and you find the critical point. So you might say that the critical point here is 0, 0, or here it's 2 minus 2, or here it's 4 comma 3, okay? But you don't know what type of critical point it is, okay? So that's what we'll do next time. All right, thank you.